In this video, we are going to talk about some multiple choice questions in organic chemistry. The oxidation of an organic compound produces two gases, which turn lime water milky. Immediately you hear lime water has been turned milky, it means that organic compound contains carbon dioxide and anhydrous copper sulfate blue. And this is also the test for water. So that means there is water inside. And he says that, so we can know for sure that there's carbon in that organic compound, and then there is hydrogen in that organic compound because of the carbon dioxide and then the water. And he says that when the compound was heated with sodium metal, so you can see that this is the Lansing sodium fusion test. The acidified filtrate, which was heated with silver nitrate to deep yellow precipitate. So you can see this is a deep yellow precipitate. Now, deep yellow precipitate is a qualitative analysis for iodine. Now, anytime you find a yellow precipitate in a qualitative analysis, which is insoluble in excess ammonia, then it talks about either bromine or iodine. However, bromine forms a yellow precipitate, but an iodine forms a deep yellow precipitate. So the deep yellow is talking about the iodine. And he says that to another filtrate which wasn't acidified and heated formed a black. The black precipitate speaks about sulfur compounds. So he says that formed a black precipitate with lead acetate. So there is sulfur in the compound. He says all other elemental tests proved negative. What are the possible elements contained in this compound? So the possible elements are carbon, hydrogen, iodine, and sulfur. So if we check through, this is carbon, hydrogen, iodine, and nitrogen. It's not true. Carbon, hydrogen, bromine, and sulfur. That is not also true. Carbon, hydrogen, iodine, and sulfur. Yeah, so the answer is E. How many stereoisomers has the structure below? Now, let's determine the stereochemistry in this molecule. If you come here to this carbon, you see there's a methyl group here and a methyl group here. So this is not a stereogenic center. And then when you come here, there's a proton here. Now this carbon is different from this carbon, which is different from this oxygen, because they all have different atomic numbers, and therefore this is a stereogenic center. If you take this carbon is different from this carbon, which is different from this bromine, and then there's a proton here, so this is also a stereogenic center. If you take this carbon is different from this carbon, which is also different from this oxygen. There is also a proton here, so that means that this place too is also a stereogenic center. Now, if you take this carbon, there's 3 protons which are all equal, so this carbon is not a stereogenic center. So we only have 3 stereogenic centers on this molecule, and the number of stereoisomers is given as 2 exponent n. So this is equal to 2 exponent 3, and 2 exponent 3 is 8. So the answer is 8. Which of the following is not true about bromination of methane? Now, let's look at the bromination of methane. This is a radical reaction. So in the initiation step, the bromine radicals are produced. So we will have these bromine radicals that are produced in the initiation step, but it is coming from bromine gas. Then in the propagation, we have this bromine radical, one of them, will come and react with the methane, and it will give us hydrogen bromide, and then methane, the methyl radical. And in the termination step, you see that we have this methyl radical, so they can combine. Two methyl radicals can combine to form methane as CH3. So let's use this to then answer the question. It says that A, ethane is formed as a byproduct. That is true because you can see that ethane is formed. Then the mechanism is a free radical substitution reaction. That is also true. Then C, energy from an external source is needed in the propagation step. That is not true. The only place energy is needed is the initiation step. Now, when you produce the radical is highly unstable, and therefore this reaction will continue without the supply of any energy. So this is the false statement. And let's check the other two statements. It says that all four hydrogens of methane can be substituted by bromine. That is true. So that in the end, we'll get CBr4. And then the last one, he says that bromine radicals are formed at the initiation step. That is also true. So the only false statement is C. In the halogenation of alkanes, what is the characteristic of the radical chain termination step? A. Radicals are formed at the initiation step, not at the termination step. Then B. Substitution products are formed. That is not also a strong answer enough. And then C. A radical reacts with a molecule to give a new radical and a new molecule. I'm talking about the propagation step here. And then D, he says that two radicals combine to give a new molecule. This is true because that is what happens in the termination step. And then E, a radical will be very reactive. That does not happen at the termination step. So the answer is D. What is the IUPAC name of the compound below? So let's try and name this compound. So if we start here, we will get the numbers correctly. So 1, 2, 3, 4, 5, 6, and then 7. So we are talking about heptane. Then you see that we have an ethyl on carbon number 4. So we have a 4-ethyl. And then apart from that, we have 2 methyl groups on carbon number 2. So we have 2,2-dimethyl. So let's combine the name. You see that E comes before M in terms of alphabet. And therefore, the name is 4-ethyl, then 2,2-dimethyl heptane. So that is the name. So if we come here, here's 2,2. No, that's just wrong. So these are the only. So having done this, we could even cancel the wrong answers. This one starts with 2,2-dimethyl. So this is wrong. So this one too is also wrong, 6,6-dimethyl. And then this one too is also wrong, 2,2-dimethyl. So the possible answers is between B and then D. B is 4-ethyl 2,2-dimethyl heptane. And that is the answer that we got. So the answer is B. How many hydrogen atoms are there in nonene, a linear hydrocarbon? You know that the straight chain alkanes are measured by this formula, CnH2n plus 2. So that means that the number of hydrogens is given by the formula 2n plus 2. Nonene means 9 carbons, so n is equal to 9. So H is equal to 2 times 9 plus 2. This is equal to 18 plus 2. And 18 plus 2 is 20. So the answer is C. How many chiral centers are there in the molecule below? Now, there are 2 protons here. So this carbon is not a chiral center. This one too also has 2 protons. So this carbon is not also a chiral center. And then now if we take this carbon, you see that this carbon is different from this one, which is also different from this carbon. Therefore, this is a chiral center. And with this one too, this carbon is different from this one, which is also different from this carbon. Therefore, this is also a chiral center. This one has two protons, so it is not a chiral center. This one also has two protons, it is not a chiral center. If we take this carbon is different from this one, which is different from this one. And therefore, this place 2 is also a chiral center. If you take this carbon is different from this one, which is also different from the OH. And this place 2 is also a chiral center. This one has two protons, it is not a chiral center. This one also has two protons, it is not a chiral center. If you take this carbon is different from this one, and which is different from this carbon. So this place 2 is also a chiral center. And if you take this carbon, you can see that this carbon is different from this carbon, which is also different from this carbon. And therefore, this place 2 is also a chiral center. But this one has two protons here, it's not a chiral center. This one too has two protons, it's not a chiral center. And then this is an alkene. These two are not chiral centers. So the chiral centers are 1, 2, 3, 4, 5, 6. So there are 6 chiral centers in that molecule. Identify which of the following is not true of enantiomers. They have the same boiling point, that is true. Melting point, that is also true. They have the same specific rotation. Specific rotation is false. Enantiomers don't have the same specific rotation. And then D is density. It's true, enantiomers have the same density. And E is chemical reactivity towards a chiral reagent. So the only one that is not true of enantiomers is specific rotation. They rotate plane polarized light in opposite directions. If a solution of a compound, which is 30.0 grams per 100 mils of solution, having a measured rotation of plus 15 degrees in a 200 millimeter tube, the specific rotation is. Now, specific rotation is given as the observed rotation divided by the concentration times the path length. So let's calculate the concentration. Concentration is equal to mass over volume. Now, from the solution, we're given the mass as 30.0 grams divided by the volume, which is 100 mils. So this will give us 0.3 gram per mils. Now, the path length was given as 200 milliliters. However, the path length is supposed to be in deciliter, and you convert it to deciliter by multiplying by 0.01. So the path length is equal to 2 deciliters. So having gotten this, then we can calculate the specific rotation. So from there, specific rotation is equal to the observed rotation, which is plus 15 degrees, divided by the concentration, 0.3 grams per milliliters, then times the path length, which is 2 deciliters, so 2 deciliters. So at the end of the day, 15 divided by 0.3 times 2 is equal to plus 25 degrees. And this is the correct answer. In methyl cyclohexane, now this, if you consider this molecule, there is no double bond and there are no triple bonds. So it means that this is an alkene, single bonds, and therefore this is an sp3 hybridization. Now the answer says that ring carbon atoms are sp2 hybridized. There is no sp2 hybridized carbon here, so the answer A cannot be correct. Ring carbon atoms are sp3 hybridized, and the methyl group is sp2 hybridized. The methyl group is also sp3 hybridized, so this is not also correct. All bond angles are approximately 120 degrees. The 120 degrees bond angle is characteristic of sp2 hybridization, so this is not also correct. Ring bond angles are approximately 120 degrees, and the ring methyl bond angle is 90 degrees. This is not also true. Then E, it says that all carbon atoms are sp3 hybridized, and that is the correct answer. So the answer is E. The two structures below represent, you see that here, these methyl groups are pointing in the same direction. And here, these methyl groups are pointing in the opposite direction. So this is a clear example of cis and trans isomers. These are six. This is cis molecule, and this is a trans molecule. So the answer is cis and trans isomers. How many constitutional isomers would the chloroalkane with molecular formula below have? That is chlorobutane. So let's try and draw there. So this is butane. So this one is 1 chlorobutane. Now we can move this chlorine to carbon number 2, and we'll get 2 chlorobutane. So here's 1 chlorobutane. And then this one is 2 chlorobutane. Then what we can also do is that we can move this methyl group here, so that we will have this molecule, which is 2 chloro, 2 methyl, propane. Now, the other thing we can also do is that we can move this, we can have this structure as well. And this is 2 methyl, 1 chloro, and then this one is 2 methyl propane. So these are the only isomers of chlorobutane we can get, and therefore there are 4. 1, 2, 3, 4. The correct answer is 4 isomers. Identify which of the following alkanes will have high boiling point. A. Heptane. B. 2-methyl-hexane. 3. 2,3-dimethyl-pentane. D. 2,2,3-trimethyl-butane. And then E. All of them. So let's try and draw the structures. Heptane, 7 carbons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then 7. Now 2-methyl-hexane. So hexane is 6 carbons. 1, 2, 3, 4, 5, 6. And there's a methyl group on carbon number 2. And 2,3-dimethyl-pentane. Pentane, that's 5 carbons. 1, 2, 3, 4, 5. So on carbon number 2 and carbon number 3, we have methyl groups. And this one is 2,2,3-trimethyl-butane. So let's draw a butane. This is a butane. So we have 2, 2, which is 2 methyls here, and 3. Now, there's one thing that is evident. All of them are isomers, actually constitutional isomers of heptane. Now, for the alkanes, you can see that there has been increases in branching. This one has 1 branch, this has 2 branches, and this has 3 branches. When you increase the branching in an alkane, you lower the boiling point. And therefore, the one with the highest boiling point is the one that is less branched. And therefore, the one that is less branched is the heptane. Choose which of the following functional groups contain a carbonyl group. And what is a ketone? This is a ketone, where R is hydrocarbons. And then ester. This is the structure of an ester. The R's are hydrocarbons. And then carboxylic acid. Now, for a carboxylic acid, this part is not joined to a hydrocarbon, rather it is joined to a proton. And then an amide. This is the structure of an amide. Here's NH2. Then, so you can see the carbonyl is C double bond O. Now you can see that here C double bond O, this one too is C double bond O. The same here and the same here. So all of them have carbonyl groups in them. So the correct answer is all contain carbonyl groups. How many primary, secondary, tertiary hydrogens are there in the molecule below, in the alkene below? So you see that this is CH3. So there are 3 protons here. There are 3 protons here. There are 3 protons here. And then there are 3 protons here. However, CH3 is talking about primary protons. So these protons are primary protons. This one too are primary. This is primary. And this is primary. So the primary protons are 12 protons. Then this one, this place, there's a proton here and there's also a proton here. Now CH is tertiary proton. So the tertiary protons, there are 2, so 2 tertiary protons. But there is no CH2, so therefore secondary protons are 0. So now if we come to the column for the secondary protons, this is the only place where there is 0 secondary protons. And if you check 12 primary protons, that's what we got here. And 2 tertiary protons. And it's the same thing we got here. So the correct answer is C. Which of the following is true about chiral molecules? A. All chiral molecules have achiral centers. That is not true. Then B. All molecules with chiral centers are optically active. This is not also true. The reason is because of the meso compounds. They have chiral centers, but they are optically inactive. Then C. The enantiomers have the same boiling point. This is true. The physical properties of enantiomers, such as the boiling point and the melting point, are the same. So the answer is answer C. However, let's check the other answers. Equal mixtures of enantiomers have the same boiling point as one form of the pure enantiomer. That is not a true statement. And then E. All organic compounds are chiral compounds. This is not also true. So the only true statement is enantiomers have the same boiling point. What is the effect of a soluble impurity on the boiling point of an organic compound? A. No effect on the boiling point temperature. A is not true. Impurities increases boiling point of an organic compound. Then B, he says that increase in the boiling point temperature. So you can see that the answer is B. There's an increase in the boiling point temperature. Let's look at the other options. Increase in the melting point range. The question is about the boiling point. There is no mention of the melting point, so this answer cannot feature. And then D, decrease in the boiling point temperature. It's rather an increase in the boiling point temperature. And then E is B and C. So the correct answer is increase in the boiling point temperature. Which of the following structures is the odd one out in terms of R and S nomenclature? So let's determine the configuration of these molecules. Now, with this one, you can see that in terms of atomic number, the highest is the bromine. So bromine is number 1. Then followed by this methyl group, number 2. And then ethyl group, number 2. And then methyl group is number 3. And then the proton is number 4. Now, if you cover the side of the proton, this is 1, 2, 3. So it's going in the anti-clockwise direction. Notwithstanding, because the proton, which is the least group, is pointing towards us, we need to invert configuration. And therefore, instead of an S, this is an R configuration. If you come to this side, the bromine is number 1. Then the ethyl is number 2. Then the methyl is number 3. And then the proton is number 4. However, proton is neither pointing towards us nor pointing away from us. The rule says that we should swap the one that is pointing away from us with the least group. And therefore, here becomes number 4, and this becomes number 3. And when we do this swap, the rule also says that we should swap the other two. Therefore, this becomes number 1, and this becomes number 2. So if we cover 4, then this becomes 1, 2, 3. So it's moving in the clockwise direction, and therefore this is an R. And if we come to this one, bromine is number 1, and then the ethyl group is number 2, and then this is number 3. So if we check it, this is 1, 2, 3. It's pointing in the anti-clockwise direction. However, proton is pointing towards us, so we need to invert configuration, and therefore this is an R configuration. So by default, since in terms of nomenclature, we've gotten RRR for 1, 2, 3, then we can say that the correct answer is 4. Let's check the nomenclature of 4. You see that this one is 1, and this is 2, then this is 3, and then the proton is number 4. The least group is not pointing away from us, so we need to invert configuration. Now, if you cover the least group, you can see that this is 1, 2, 3. It's moving in the clockwise direction. But since we must invert configuration, then this is an S. So the only odd one out is the answer D, which is the 4, this one.